welcome everyone to the ICS Theoretical Astrophysics Seminar. So this week, we are very happy to have Julian Adamek, who is going to talk about general relativistic N-body simulations for cosmology. So Julian did his PhD in Wolfsburg, and then Würzburg. So sorry, Würzburg, and then postdoc in Geneva, then in Paris, then in Queen Mary, London, and now we're very glad to have him as an Eccellenza professor at ICS. And so, Julian, we're listening. Thank you.
Thanks a lot. It's a great pleasure to join you here at the Institute. So what I'm going to do today is to give really an overview talk of the context of my research, how all the journey until I came here, and things that I'm going to do hopefully in the future here. So for this title slide, I'm showing a picture that I also showed at the interview at the SNF for this position, which I think is a really nice illustration of the situation we are facing. So you can see here on the left side, maybe some of you have already recognized what this is. This is at the Lake of Zurich, and a photograph taken from the International Space Station. And just from the distribution of the lights, you can kind of make a guess about the geography of the underlying landscape. And here on the right-hand side, I've overlaid a simulation where you can see a little bit of large-scale structure. You see these light spots here are halos. And so we're trying to do something kind of similar. We have only the light that we observe in the universe, and it only kind of traces a little bit the underlying geometry, and we are trying to deduce something about the geometry of our universe. So this is what I want to do. Just kind of another motivation slide here. Probably you've often heard people saying we are doing a precision cosmology. We've been doing this for more than 15 years now. I think since WMAP gave us a measurement of the CMB anisotropies, we can really talk about precision measurements. But I think we are now entering a new phase, and this new phase really comes with big data. So what is really new is that we will have these upcoming surveys here. So ground-based stage 4 surveys, so-called. So they do really like observe galaxies out to very large distances, very large volumes, billions of galaxies, spectroscopy, and so on. Then of course there is Euclid, which people here in the institute are very active participating. This is a space telescope that ESA wants to launch in, well, a bit less than 2 years from now, hopefully. and that will also take huge amounts of data. So like the return downstream will be something like 100 gigabytes per day, and it will observe several billion galaxies. And this is really a game changer in the sense that we have so much data that we can try to look for very small effects in the statistics of the distribution. This is something we couldn't do 10 years ago or something like that. Okay, so one thing that we can do with this data is to think about if we can do new tests of gravity. So here's a small illustration of what kind of tests of gravity we've been doing in the past. So of course you can do laboratory tests. You can measure the gravitational redshift, let's say, with a tabletop experiment. So if you put an atomic clock on the floor and you put one on the table, you can actually measure the time that the clock on the table actually goes a little bit faster. So that's what you can do with atomic clocks. So you measure on the meter scale the gravitational field. We have, of course, solar system tests, standard tests of gravity like perihelion, advance of Mercury. Famously, this is also a Nobel Prize. We've been observing pulsars, and their change in the period was very strong evidence that general relativity was correct, because you could see that some gravitational waves are radiated exactly the same exactly the correct rate. And since now a couple of years, famously, we have the LIGO, Virgo observations of gravitational waves directly here on Earth. And here we are able to probe really the strong field regime of general relativity. We really see the point where the two black holes merge. Okay, so you can see that we have quite a, like from the very weak, like laboratory scale, very weak field regime up to the strongest field regime we can imagine. We have covered this range, but in terms of length scale, actually this is kind of relatively modest range of scale. So we can go from meters to solar system scales. All of these systems are smaller than the solar system, so we don't really have much data beyond the solar system scale. And this will change, I think, if we go looking at large-scale structure. So here we are in a new regime. We are in the weak field regime, so very large scales, and we are probing an entire new regime because in the large-scale structure we have all these voids, and these are the only places in the universe where dark energy dominates. So on all these scales here, we are not really able to probe anything about dark energy. You know, dark energy is this mysterious phenomenon that the universe expands at an ever increasing rate. And if this has anything to do with gravity, large-scale structure is the thing where we have to look for for an answer. So just to give another illustration of this aspect of how we test gravity on these extremely large scales, this is again kind of to give you a better intuition. What I've plotted here is a map of the world, obviously, that you get if you put yourself in the position of Zurich, and you just look in any direction and go along a great circle, and then ask, okay, what if I go into this direction along the great circle? What a certain distance? So everything is at a correct great circle distance measured from our position here in Zurich. Okay. So what you can see is that if you are local, you're staying local. Let's say you look at just Europe, the distance between London and Berlin, you still get quite right in this map. But once you go to very large distances, because the Earth is curved, this kind of mapping will distort distances. So the distance between Rio and Cape Town, for instance, will be like much exaggerated here. And something similar will happen, because this is really a little bit how we observe the universe, right? So we are sitting in our small observatory here, and we measure the directions at which we see galaxies, and we have a distance indicator, but somehow the light comes to us through a kind of perturbed geometry, and that will lead to a kind of deformation of this map or chart that we create of the universe. And we can look for the effect of this deformation, and then learn something about the gravitational field. Okay, so from the numerical side, so I do, as already the title implies, I do N-body simulations in general relativity, and the numerical challenge that we want to address in these simulations is summarized here. So first of all, in order to be useful at all, I think, in terms of simulations, you want to kind of follow the fully nonlinear evolution of matter. Otherwise, you can do perturbation theory. You don't need a computer. And we choose the N-body method because that is, at least for the cold dark matter scenario, the best suited that we know, at least. And then, in order to do all this amazing gravity tests, right, you also want to consistently solve the evolution of the geometry. Second ingredient. Now, as I just hinted at in the previous slide, there is this this problem that, okay, you can maybe simulate the universe, but then you also have to think about how you observe the universe, right? So we actually also want to map the simulation results to actual observers. So we want to tell, in the end, what does the, and like a simulated observer inside our simulation, what does he really see? So there you can use, for instance, ray tracing to kind of generate a chart of the universe. And because we go beyond, because we are looking for very small effects, I think we are also now in a place where we have to think a little bit going beyond cold dark matter only simulations. So here are just a few things that come to mind. First thing, many people, of course, here in this room are working on this, like what happens at small scales, baryonic effects, and so on. I'm not going to talk about this at all, because I think in terms of testing gravity, this is really a regime where you would be probably a bit pessimistic. You really, in order to do a clean test of gravity, you want to go to very large scales where there's only gravity active, right? And you don't really care about astrophysical processes, but you don't really have good control over. So I'll just cross that one out and look at what happens at large scales. And at large scales, there are still a few interesting aspects. For instance, cosmic neutrinos, they have a very long free streaming scale. So they do something at the gigaparsec scale. They still have an effect. So you should include them, and we do. And could also do other relativistic species. I don't know, dark photons or whatever, even normal photons. And finally, once you want to go beyond lambda CDM, you could also think about dynamical dark energy models. They can also, in principle, if they have, let's say, they have like dark energy could have perturbations. If the sound speed is large enough, will have effect on large scales. So here you also want to include this effect. And we want to do all this, of course, while at the same time not being like confined to, I don't know, 100 cube simulations, because otherwise it becomes too expensive. So we have to kind of maintain a competitive performance and scalability on the machines that we have. Okay. So a couple of years back in 2015, we started to attack this challenge. I was a postdoc in Geneva at the time, working with Ruth Dürre, Martin Kunz, and Martin's PhD student, David Alverio. And we made the first release of this, whoops, where's my mouse now? Of this N-body code called gevolution. I'll just show you, whoops. I want to show this. Yeah. This is just like one of the little videos we did at the time, showing a simulation that we did with the code. And maybe you can see here, I have to play it again. So these stripy features here, or this shows you in this simulated box the gravitomagnetic potential, so the frame dragging effect in the universe caused by the presence of large-scale structure. Right, just one last time. Right, and all these little dots here, this is just different halos. Okay, so you can see it, of course, is kind of correlated with large-scale structure, because large-scale structure is how it forms. So now, how does it work? How do I get out of here? Okay, great. Just to summarize some of the numerical aspects of this code. We are now at version 1.2, so it's a bit upgraded compared to the one that we published originally in 2016. It's a particle mesh N-body code. So what this means is that you have a particle ensemble, and for the metric part, so the fields that describe the geometry of the universe, we have a mesh, which is sampled on a fixed grid without refinement. And yeah, so if you want to know how a particle moves, you kind of interpolate the metric to the particle position. You move the particle using the geodesic equation, and then you compute the stress energy tensor of the particle ensemble, and that then becomes discretized, like with a particle mesh projection to the lattice, and then you can solve Einstein equation on the lattice. That's more or less the the way it works. I should probably stand more here that people can see me on the on the channel. So at the time we were kind of lucky that in the group we had David Averio, who was for a different project working on this lattice code that could do fast Fourier transforms. I've just shown here like an illustration how the parallelization works in this lat field 2. You have your cubic domain, and it's then for each MPI task you kind of split it up like this, and the point of this distribution or parallelization is that you keep one direction in your spatial domain local for the MPI task, so you can do a FFT very easily. And then if you want to do a 3D FFT, you have to do 2 transpositions, right? First direction, then you do a transposition, which means MPI communication along this direction. Then you do another FFT, and then you do the same for this third direction. And this this really scales up to hundreds of thousands of processes, really very efficient. So since we had this and said, well, this is really cool, we can maybe use Fourier methods to solve Einstein's equations with this. We asked David to add a particle handler to the code, and then we could use it for our N-body code. So that's more or less his role in the project, summarized. On terms of the front end, I try to do my best to kind of conform with industry standards, which makes it kind of hopefully very easy to use the code. First of all, the way you kind of pass parameters to the code replicates exactly class syntax. So if you have ever run class, which is a widely used Einstein-Boltzmann solver, the way you pass parameters to gevolution is exactly the same. And for all the parameters that have kind of a physical meaning, also the meaning is the same. So you can actually write a settings file that you can give to class. It will give you the linear prediction. You can take the same settings files, pass it to gevolution, will give you the nonlinear prediction. Okay. Without even changing one line in the settings file. Then for the outputs, well, you can do snapshots and also particle light cones. They are both in the gadget 2 binary format, which you can again easily use with all kinds of tools that have been developed. Snapshots of the mesh quantities, which are just 3-dimensional arrays, really, are stored in HDF5 format. And finally, for light cone output of the metric, so for instance, the gravitational potential, frame blocking potential, and so on. If you do it on the light cone, because of the geometry of the light cone, it's more conductive to have kind of spherical coordinates, right? You know, the observer looks at the metric down the light cone at different, like spherical shells, let's say. And so it's discretized using Hilpix maps on spherical shells. Okay. And that is then, and I'll talk a little bit later about this, very useful for ray tracing, because, yeah, well, I'll talk about it later. Good. Now let's talk a little bit about the physics behind all this. So if you want to, so what we want to do is to solve general relativity. And yeah, the starting point is this Hamiltonian formulation of GR. And it's really a very natural way to start, also from a simulation point of view, because so what this means is that you foliate your space-time into space-like hypersurfaces. And when you do a simulation, you already kind of do this, because you're doing a time evolution of a spatial configuration, and every time step of this simulation is effectively a spatial hypersurface, if you think about it this way. And so you can write down the 4-dimensional metric decomposed with in this way. So you have, for the time component, you have this lapse function alpha, and then you have for the space-like metric, you have this gamma ij, and then there's this shift vector beta. So this is really fully general. You can always do this. And now you have to choose a gauge. So we choose the Poisson gauge, which is really very useful in the weak field regime. And I'll explain a little bit what this means in a second. So here the lapse function, you write like e to the psi times the scale factor, then here the space-like metric e to the -2 phi times the scale factor squared, and there is a small tensor perturbation here, and here this is the frame dragging potential with also a spin 1 field, so there's no divergence here. That's the gauge condition. So you have two scalars, psi and phi. You have 2 vector degrees of freedom hidden in here, because this is divergenceless, and you have spin 2 degrees of freedom in there, because this one I require by the gauge condition to be transverse and traceless. And you might wonder, well, what is the significance of the scale factor here? And always people were wondering, so now are you telling me that you are background dependent? This is not really an additional degree of freedom. You can see that if I would change the scale factor by something, I can absorb this change by absorbing into the phi, phi, and the frame dragging potential. So it's just there to make the connection to perturbation theory, right? You could just ignore it, and then you would just have like a large, essentially log A addition to this potential, but you just take it out of the equation, because then the equations become nicer and more recognizable. But in the end, you just plug in this ansatz, and whatever A you use, if your real evolution of the universe would be something slightly different, it will be taken up by these potentials automatically if you solve the equations consistently. So that's all there is to it. It's not just a choice of variables in the end. Okay, so now the next thing we are going to do is to exploit that we are in the weak field regime. And what I mean by this is that if you look at these different perturbations of the metric, you can do perturbation theory, and you will find that if you compute, this is the dimensionless power spectrum. So you take the 2-point function and Fourier transform that. And if you look at perturbation theory, so these are these dashed lines here, by far the largest contribution comes from the scalar gravitational potential. It's this curve, so it's about 10 to the -5. You have to remember that the power spectrum is a quadratic quantity, so take the square root of this roughly, then you get roughly the size of the object itself. So it's 10 to the -5 on most scales. And then the next one would be the frame dragging potential, which is already like 4.5 orders of magnitude below that. So you have to do a second order calculation, by the way, to get this curve, because at first order it vanishes. And then beyond that, you can look at the difference of the potentials. It's called gravitational slip sometimes. And that is even much smaller, like another 4 or 5 orders of magnitude. And spin 2 field created by the large scale structure is also very, very small. So so that really motivates to say, okay, well, actually, we want to keep these because we want to do GR, but why not linearize in these terms, right? We can linearize our field equations in these terms. They're really, really small corrections, but everything else we keep nonlinear. Okay. And just to explain what these colored curves here are, so this is for different redshifts as well. These colored curves are if you then do a simulation and you compute these objects nonlinearly, like solving the Einstein equation, you get some corrections on small scales because there's nonlinear structure that actually produces some more frame dragging and some more gravitational slip and so on. But it's still, I mean, you can see it's still very, 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 very small. Okay. So with this in mind, so good point. So this gray is just for people wondering how to interpret this. I plotted the primordial gravitational wave background for a scalar to tensor ratio of 0.1. So this is the primordial gravitational waves. They kind of have nothing to do with structural formation. They are created in inflation. If they are created, we don't know yet. And this is more or less what we are hoping to be able to detect at some point. 0.1 is like the limit that we have at the moment. And you see that the large scale structure doesn't really produce something above that level.
Ratio is 0.1.
Yeah.
That's a scalar to tensor.
Yes. Yeah. Yeah, but you have to, so first you have to remember that this is at redshift 3. So that this one, you can see it goes down with time. So the scalar to tensor ratio means that outside of the horizon it actually is. So if you go up here, somewhere this becomes flat. And there you will see a 0.1 ratio. Yeah. Inside the horizon, the gravitational waves just decay. Okay, anyway. So now with this in mind, you go to Einstein's equation and you just write down the left-hand side and linearize in this, for now, in the frame dragging potential. This psi is just phi minus psi, a new variable, phi minus psi, which is also very small. So we linearize in that, and we also linearize in the spin 2 field. And for the gravitational potential itself, we could go fully nonlinear, but we chose to do something like this, where we only go to next to leading order. So we keep terms that are multiplying things. So if there are two derivatives, let's say in a term, then we keep the quadratic term as well. The reason is that this thing, for instance, can become very large, right? So keeping this term, well, might be justified in some regime. You can also think about this in terms of if you look at like a compact compact structure, and you would get if you solve these equations, you would actually get the correct post-Newtonian, first order post-Newtonian potential corrections. So something that gives you the perihelion advance, let's say, right? That would be included here. Even though the simulations are probably not not precise enough in terms of resolution to ever get there. Anyway, so so these are the Einstein equations written down once you have expanded in this weak field variables. The stress energy tensor is kept fully nonlinear. There's no approximation there. And so let's just quickly talk you through this. So you can see that you have here a parabolic equation, let's say, with the two potentials, phi and psi in there. And here, if you look at this equation, it's an elliptic equation again, with psi and phi in there. So these two equations together determine the gravitational potential. Then we have another constraint from the momentum constraint that gives you the frame dragging. And then finally, the spin 2 field would be a wave equation with some source. So you can put this on the other side if you want. Once you have solved for it, you have a wave equation, and yeah, so that would give you the gravitational waves or spin 2 perturbations. Let's say, because there's really thinking of it in terms of gravitational waves is a bit misleading, because in cosmology you're not in the far field, never, right? You have sources everywhere. You're looking at large scale structure, and so it's really a spin 2 perturbation of the metric that doesn't propagate, really. It is just imprinted by the large scale structure. Yeah, it's in psi. So psi is phi minus psi. Yeah, but this one is really small. Yeah. Chi, sorry, yeah, chi. So this we take this as a new variable called chi. Chi, yeah, great. Okay, so good. So now let me talk about the right-hand side a little bit of the Einstein's equation. Yeah. That's dTau, the conformal time.
And so if you now want to cross out the term that gives you back the Newtonian phase.
Good. So first of all, so on small, because we are in the Poisson gauge, we are not really in the same gauge as a large Newtonian simulation. We can talk about this later. But let's say we go to small scales where gauge doesn't matter. And the Newtonian limit you get by, first of all, linearizing this. So this one goes away, this one goes away. And this one goes away because it's only at large scale. So gauge, this one goes away because also only at large scales. So you really are left with this term So Laplace phi equal density contrast.
Yeah. Okay, the prime, I understand, because usually the time directly with respect to the Hubble is very small, right? But the H square.
So the reason.
Very small here is tau, right? It's not tau.
This is small. This is small, and the reasoning is so this term is small compared to this term on small scales.
Okay.
Yeah,
so
yeah.
You're much below the horizon.
Yes, yes. And if you are close to the horizon, these terms will be important, and they are gauge dependent terms. So you can gauge them away. If you go to a different gauge, they will disappear. Yeah, yeah. Yes. So for the stress energy part, we have, of course, first of all, the N-body ensemble. And there, again, keeping fully within general relativity, you start with the one particle action. This is really what it is. Then you can, again, switch to a Hamiltonian picture. So you introduce a canonical momentum. And then the geodesic equation is really just the set of Hamiltonian equations of motion. So you get the update of the position is given by this, and the update of the momentum is given by this. You can do a leapfrog, okay? And you can, of course, taking like, how do you say, if you vary the action with respect to the metric, you get the stress energy tensor, and then you can, again, you solve these things for the canonical momentum, and you can write the stress energy tensor. I just wrote the 0,0 component, but you can do it for all components. You can write it in terms of the canonical momentum. Okay, so this is again now linearized in B and HIJ, but fully nonlinear in the canonical momentum and in the potentials. Okay. So you can, the nice thing is you don't have to assume low velocities here. You can use this, for instance, for neutrinos as well. It works up to ultra relativistic limit. You can have Q square much larger than M square.
It contains special relativity.
Yes, yes, it contains special relativity. That's correct. Yeah, and you see that. So if the momentum goes very low, you will see that this whole thing this whole bracket here more or less just becomes a mass, right? But then if you go to very high momentum, you see that actually you get yeah, exactly. Okay, so here you have the particle update, and here you have how it feeds into the computation of the metric. Okay, now you can do the same thing for photons. So for photons, you also just get a geodesic equation here. Now, for now, I dropped the terms that contain the HIJ because later we will actually neglect them in the ray tracing, just because we are lazy. You can put them in there. It just makes the computation more a bit longer. But you will find that actually, if you think about the size of these terms, right? So you have like the gradient of the potential, and then you have here the gradient of the frame dragging potential. The frame dragging potential, I said, you saw in the other plot, is about 4.5 orders of magnitude in the 2-point function down. So if you take the square root, it's about 1%. Okay, and then if you would add the HIJ term, there's another some orders of magnitude. So you're talking about like the 6 or 7 digit once you sum up all these terms, you're changing the 6 or 7 digit. Sometimes you're even reaching kind of the machine precision, so kind of pointless to even add the term, right? Okay, so you have the geodesic equation of the photon, and then what you can do. So if you've done your simulation, you have maybe I didn't explain this yet in great detail, but so what the simulation or what the code allows you to do is to choose an observer, and then for that observer the null hypersurface in the background, right? That is their path light cone, and then whenever you have the particle word lines that kind of evolves through the simulation. Once a particle word line crosses this null hypersurface, you kind of record that particle. So you do this for all the particles. You have a particle light cone. And then you can, for instance, run a halo finder on this, and then you have something that you can say, okay, this is my mock survey or my population of sources on the light cone. And now for the metric, you do a similar thing. You still have this null hypersurface. So at every time step, your hypersurface will kind of cut, your equal time hypersurface will cut through this null hypersurface. And there is kind of a region that is interesting for ray tracing, and you keep the metric in a kind of a finite region around the null hypersurface. Okay. And the point of this is that you can take derivatives of the metric, and you can actually wander a little bit off the null hypersurface that you would have in the background, and you can do ray tracing without any approximation. So you start at the observer, and you solve this equation backwards in time, and you have enough data that you can always compute these terms. And you just solve until you shoot towards your halo, let's say, and then your light ray will be deflected, and you will miss the halo. Okay. Because you have also the velocity of the halo, you also know like a tangent of the world line of that halo, and then you kind of, by shooting, you kind of try to meet these two geodesics, right? That they meet in one event. So with a few iterations, you are there, and you have the observed position and the observed redshift, observed distance, and so on of this object. Really non-perturbatively, if you want, to arbitrary high order in perturbation theory, if you want. Okay. So this is what we worked on for the years after I left Geneva. And now the first thing we did with this, so I'm going to go through a few examples what we did in the past with the code. And so we did a big simulation with a huge light cone, did a halo finding. We have like, this goes out to redshift 3 point something, 24 or something like that. And there are like 10 million halos there, down to Milky Way size. It covers 1% of the sky. And then we did a ray tracing, okay? And we didn't only solve the null geodesic equation, we also solved the geodesic deviation equation, which then gives you the deformation of the light beam, right? So you don't only get the position of the object, but you also see what is its angular distance or luminosity distance, and what is the, let's say, the ellipticity. If the source would have a spherical shape, it gets a little bit squished because of lensing. So we did all this, and if you just take the luminosity distance and plot it versus the observed redshift, so these are both really the observed luminosity distance, truly observed redshift. And then, of course, you have, you are kind of in a lambda CDM model. You plug in in the background the relation for any given redshift. You can compute the luminosity distance, and you can plot the residual. And this is what is done here. So each little dot here is one source. And you can see that you will have here that you can, in the beginning, very locally, you will see a little bit of structure because you have local phenomena, and then it just becomes a very broad distribution. And it's asymmetric. So here you will see that you will find few sources that are very highly magnified. So the luminosity distance is quite a bit lower, but not the opposite. You don't find something that is hugely demagnified. And the reason is just that the magnification is done by voids, and magnification is done by halos. And halos can become very compact and massive, and voids can only become empty. And then when they are empty, they cannot get more empty. So there is kind of a empty beam limit that you could plot here that is somewhere here probably, that you cannot really cross. Yes. That's for halos. That's the 10 million halos. Yeah. Well, yes, yeah. And the mass limit is more or less chosen by the resolution limit. So that at some point you just can't resolve halos anymore. Okay, so now we understand a little bit why this is asymmetric. And now, if you want to ask what would I measure as a Hubble diagram, the question becomes, yeah, okay, now you have the scatter. Now you can average Like you bin this data and you average, but what do you average, right? So here are a few choices. You can average the luminosity distance, the distance modulus, the flux, right? And because these are nonlinear functions of the luminosity distance, the average will depend on what function you choose. So here you can see that some of these averages, if you average the wrong quantity, will bias you, right? And the one that is least biased is maybe a bit unsurprisingly the flux. So if you average over the flux of the sources, you get something that is very close to the one that you expect in the background. Now you can run an MCMC to kind of constrain the cosmological parameters from this Hubble diagram. And here what we really did was very simplistic. We assumed a Gaussian scatter, which is of course not very accurate here. And then just ran the MCMC, and you see that whatever you do, whatever quantity you're looking at, you get a biased result. So then obviously you say, well, but Gaussian assumption was not good. What do you do? What you can do? Well, you just take number of points together and first average over them, and then their average is more Gaussian. The scatter of that average is going to be more Gaussian because of the central limit theorem. So the Gaussian approximation becomes good. You blow up a little bit your error contours, and you see that you still, after the spinning, can be biased if you use the wrong quantity to average over. So we found that if you bin the data so that it becomes Gaussian, and if you use the flux, you are going to get an unbiased answer. Yeah. Yeah, you run an MCMC, and you have to put a likelihood model. So you have your cosmological parameters, and then the Gaussian likelihood model had a few parameters that were also fit jointly with the cosmological parameters here. So we didn't put by hand what is the best Gaussian that represents this data, but we kind of let the MCMC determine by itself what is the best Gaussian likelihood that you can find for this kind of distribution, right?
You could also have the actual distribution.
That would have been better. That would have been better. Yes. Yes. Yeah. I don't know. Maybe if you know exactly the distribution, you can shrink the error contour a bit. Yeah. I don't know.
So just to understand, this effect of the spread is due to mostly the metric situation.
Yeah. And also the redshift. Yeah.
Exactly. So there is no, just to connect to what you said before, right? The effect of P of the same value effect is 1% of the
of the lensing. Yeah.
Here, really, if you neglect P, all this, you will find something.
Yes. Yeah. I think it would be very interesting to think about an observable that is specifically sensitive to B, but it's kind of difficult because it will give you a small correction to the lensing, but yeah. And the lensing itself is very difficult to measure. You want to have a 1%, and you want to have an observable that's specifically sensitive to this 1%. So you have to be clever. Yeah. Okay, how much time do I have? Yeah. I think that's the easiest answer, I would say. How much time do I have? 15? Well, okay, yeah. Then I'm really good because I have only 2 more examples to go through. Okay, the next example I want to connect to this this point that I made earlier about the charting of extremely large scales. And here we thought about the problem that's okay if you do this ray tracing, and people, I mean, we were not the first to do ray tracing, of course, other people have done this as well. And so if you do this in a Newtonian simulation, it's very common that people will just use anyway the Poisson gauge lensing formula. So you use effectively this without the b. Okay, just maybe you linearize in phi. You get a lensing formula out. That is the one that you find in textbooks and everyone uses. And on small scales, if you remember my earlier picture, if you have small distance scale, it really doesn't matter in which gauge you are. So you can works very well out to probably the equality scale or something like that. Or maybe not quite, but yeah, let's say a gigaparticle. I would trust this, but because the Newtonian simulations, they are not in the Poisson gauge, right? They don't use a really relativistic prescriptions to start with, and people have thought about this. So how do I actually, if I make a very big simulation that feels like the entire observed volume, we are close to the horizon. So how do I still make sense of this? And some clever people, most of them were in Portsmouth at the time. One of them is Christian Fiedler. They came up with the idea that you can actually use the equations that you solve in the Newtonian case as a gauge condition. So they say, okay, let's see if we can find a gauge in which actually on large scales, all the equations that I'm solving are still correct. And this is then called the N-body gauge. Or there's actually a family of gauges where N-body gauge is like one example. and you can you can think of these simulations as being that gauge. And now if you put the lensing calculation on top of this, it becomes inconsistent at very large scales because you're not in the same gauge. So the coordinates that you use in order to do the calculation for the lensing, you are connecting 2 points in this coordinate system of the Poisson gauge. And now you say there is a halo, right? But that halo that had that coordinate has that coordinate in a different gauge. So that's inconsistent, right? So you actually have to account for this. And you can, because you know the gauge transformation between these two gauges, we can see how much of a map distortion this gives you. And if you look at for instance, the contribution to the 2-point correlation function, this is at redshift 1.5. On very small angular scales, the lensing will give you a huge contribution. I don't even plot it here; it really blows up at very small separations. But if you go to large enough separations on the sky, and at redshift 1.5, you're looking at such large distance scales that, first of all, the density perturbation is very low already on these scales, and the lensing contribution also becomes low, and this map distortion kind of becomes, well, no, it's kind of similar to the lensing effect. So if you want to trust your distribution on the above 10-degree separation scales, then you should probably at some point worry about this effect. And it's actually not too difficult to include because we did this calculation and we know how to include it. Okay, so as final example, and this goes a little bit more into the direction what also plans are here while I'm gonna be here in the next 5 years, is that because you have this relativistic formulation of the whole system of equations, you can change the right-hand side of the Einstein equation, you can put some new stress energy, and still push everything to the same machinery. You haven't made really a big assumption about the stress energy at any point. So you're allowed to put something that produces large or relatively large gravitational slip, or anyway has some relativistic stress energy. And an example would be just like as a very, very simple one is clustering dark energy. So here what we did is you change the equation of state from -1, which is cosmological constant, to something a little bit less negative, and then you have evolving dark energy. And if you think about a fundamental model that could do this, is for instance a scalar field, right? It rolls down a potential. The standard one would be quintessence. That has a speed of sound of 1, so it doesn't really cluster. And now, if you kind of introduce additional terms in the action of this scalar field, you can make the perturbations propagate at a lower speed of sound. And then this is called clustering dark energy, or KSS. So we have, at the linear level, you have two new parameters. You have equation of state, and you have speed of sound. Okay, and so you can do a linear calculation. And so this is already included in the public code, because kind of you do the same thing for neutrinos, or you can do the same thing for neutrinos. You have your realization that you start with initially, and for the N-body ensemble, and now you ask, okay, now what happens if I want to add neutrinos, or what happens if I want to add something else? If the thing that you want to add doesn't cluster, like neutrinos, for instance, or non-clustering dark energy, you can get away with solving only the linear evolution of these. So you can couple your code to a Boltzmann solver that gives you the transfer functions, and because you know the initial phases of your random realization, you can just turn this into a realization at any time, and just use kind of this linear approximation of the stress energy tensor, and then feed it into your equations, and you get out the correct evolution. So this has been done for neutrinos, and you can do this for dark energy, and I think even has been implemented in a PKD graph that people have run for the Euclid emulator, also for dark energy, by the way, for the non-clustering case. So now let's think about you switch on, or you decrease the speed of sound, and well, you can still get an answer. So here, this is at redshift 0, the density of this clustering dark energy, if you just use the linear transfer functions and turn it into realization. And you see that at large scales, it kind of, well, you see, for instance, here's a little bit less density, and you also see this here. And Farbod Hassani, who's the new, or just did his PhD, now he's a postdoc in Oslo, was PhD student of Martin Kunz. He kind of implemented really the fluid equations of this dark energy field into gevolution, so that you can source these fluid equations by the true metric. So you can actually see how it really clusters. So that the dark energy field will kind of fall into the potential of the dark matter. Here's just an example. So you see here, this is dark matter. There's a big cluster there, and you see that actually, the dark energy will fall in there and will actually increase the mass of this object. And yeah, so this is really something that you can extend, and you can think about trying to include like more generic dark energy models and do full simulations to see what you get, what kind of constraints you can get on nonlinear scales on these dark energy models. And this is something that I plan to do. So exactly. So left hand is public version of gevolution, and you couple it. It is coupled to class. So it will ask class. So class, please tell me the transfer function, the linear transfer function of this dark energy density, and then it will turn it into a realization. And this is what you get. Because it's linear, it doesn't really see that a cluster has formed here. But you see, okay, there's a little bit of overdensity there because the cluster formed in an overdensity. But it doesn't really see the nonlinear structure. And here in this code, Farbod's code, or Farbod's attention to gevolution, it is, to be precise, it is the linear evolution of the field coupled to the nonlinear gravity sector, right? So we still kind of don't solve like a full model of k-essence, but like a linearized model of k-essence. But because there is these deep potential wells, it can still form a kind of nonlinear configuration. Yeah. And then going like even beyond this is like the next step. We want to, of course, at some point we want to have like fully nonlinear. We have to think about how to do this in the most useful way, because if you just focus on one particular model, it can become boring very quickly because it's just one model and who cares. So you want to have something that kind of where you can match or map different models to your kind of parametrization. That is the idea, I think. Yeah. Okay, so that was my final example. So let me just sum up. So I think the big thing to look forward is that we have this big data. which has really unprecedented statistical power. We will see very small effects that we weren't able to detect previously. And so this means that these perturbations of space-time become a signal that we can measure. And that is really the thing we want to do. And if some of these perturbations are produced by dark energy and we measure them, then we could get a clue about what dark energy is. We have no clue at the moment. So we need to hope that the large-scale structure can hopefully point to a way out. And yeah, in terms of the methods, what I've presented is a kind of a unified approach. You're just in a relativistic framework from the beginning to end. You fit your N-body simulations with a relativistic space-time. And then if you put ray tracing on top of this, you can include all the effects that you care about when you construct your observables, even without any real approximation. The only approximation is that you are in the weak field, which is always fine in cosmology. Okay, I think that's all. Thanks very much.